Swayam Prabha. Digital India. Educated India.
Jnanam Paramam Dhyayam. Knowledge is supreme.
In the last lecture, we saw that when a ring is Noetherian, a Noetherian, and V is a finite A module, then to this V we have attached two subsets of the spectrum of A. One is associated primes of V and the other is support of V. Both these are subsets of the spec of A, and we have checked that the support is actually a closed set. This is V of annihilator of V, and also we have checked that both these have the same. We have also checked that this is a finite set, and we have checked that both these sets, subsets of spec, they have the same associated primes of V and support of V, have the same minimal elements. With respect to the natural inclusion. All right. So one of the important consequence is the corollary I want to mention. This is applied to the ring. So if A is a Noetherian ring, then spec of A has finitely many minimal elements. With respect to inclusion, the natural inclusion. This is immediate from the fact that you apply the above observation to the module V equal to A. Then in this case we know spec of A equal to the support of A as a module, and then we know the associated primes. This is a finite set and their minimal elements are same, therefore spec A will have finitely many minimal elements. All right, now we want to do a little bit further more detailed study about associated primes and what is called primary decomposition. So now I want to study what is called primary decomposition. All right, so in this we will mostly assume the ring is Noetherian. So let us assume the A is always, I will not keep saying, but this is our blanket assumption now that A is a Noetherian ring. And V is a finite A module. It is generated by finitely many elements. All right, so observe that we have this, because V is an A module, we have this ring homomorphism theta from the ring A to the endomorphisms of V plus. That is A going to the homothécy. These are also, this theta A is also called homothécy by A. So this is any element x sending it to Ax. So given a ring homomorphism like that, we can define a module structure on the abelian group V plus. Conversely, if you have a module, that means we have this ring homomorphism. And this element, this theta A, is called homothécy by A. Alright, so that is the notation. So note that homothécy is nilpotent. This theta A is nilpotent. That means composition of theta A finitely many times it becomes 0. That is if and only if A belong to intersection of all P, where P belonging to the associated primes of V. This is very easy because I am going to use the fact that the associated primes of V and the support of V, they have the same minimal elements. This is what I am going to use. Alright, so and we know that the support of V is the V of the annihilator. And therefore, we know the intersection of P varies in the associated primes, also same as intersection P varies in the support. This is because they have the same minimal elements, and this is nothing but the radical of this annihilator. So that means some element A belonging to the intersection P belonging to the associated primes, if and only if some power of A belonging to the radical of this ideal means some power of that A belonging to the annihilator of V for some n in n, but this is equivalent to saying the homothécy by A power n is 0, but that is equivalent to saying theta A power n, that is composition of theta n times, that is 0. That means it is nilpotent. So we proved our assertion that homothécy is nilpotent if and only if A belongs to the intersection of all associated primes. Alright, when the next lemma I want to analyze, saying that when will the associated primes be singleton. So the same notation as above, V is a finite A module, and then I want to know when associated primes of V is singleton set. Only one prime ideal belong to that. That is equivalent to saying for all A in A, the homothécy is either injective or nilpotent. How do we prove the equivalence of this? So proof. Okay, so this condition, homothécy is either injective or nilpotent, that is equivalent to saying, so let me write it RHS, if and only if, what is that? Every element of A, so A, we know when it is nilpotent by the earlier observation, that is precisely the intersection of P P running in associated primes of V, that is nilpotent, or it is injective, and injective means that it is not in the annihilator. So that is not in the, so this is injective means union, let me write it below here, union A minus union P, P varies in associated primes of V. That is precisely the definition of the associated primes. When will it not be injective? When some P, when it will be in the associated prime, that is the zero divisors. So injective, then it cannot be zero divisor, that means no element, no non-zero element of V can annihilate that. That means it is a complement of the union of the associated primes. So that is precisely the translation of this right hand side. So this is if and only if. Now this A equal to this, but that is equivalent to saying the intersection, this P varies in the associated primes of V. This intersection is a complement of this union, this is the whole ring. So this must be equal to the union of P is in associated primes of V. So intersection equal to union, that is this, that is just a set theory. But that is precisely when can it happen? This can happen only when, so that is if and only if the associated primes is only one, is singleton. Because if there were two elements, at least two or more, then this side is smaller and that side will be bigger. So therefore it is singleton. So corollary, or moreover, let me write it as a corollary. In this case, so if LHS or RHS or equivalent RHS is satisfied, then in fact you can describe the associated primes. So associated primes of V, that is singleton, and that element, that what is that prime ideal? That precisely the prime ideal, all those elements A in A, such that the homothecy is nilpotent. That is that prime ideal. So this is the only element in the associated primes of A. Alright, so this will allow us to define something. So let me define now. So definition. So A is an Noetherian ring. And E is a finite A module. And U is a submodule of E. Submodule. Then U is primary in E if the module V, which is the residue class module E by U, satisfies equivalent conditions of the above lemma. That is, the associated primes of the module E by U is only one. It's singleton P, and in this case we will also say that U is P primary. That is more precisely. In this case, we say that U is P primary, submodulo of E. All right, let us see some examples. That is, so note that if I take a Noetherian ring, a Noetherian, then every prime ideal P is a primary submodulo of, is a P primary submodulo of A. That means what? That means we have to go mod that P and check whether it has only one associated prime ideal. So that means that is associated prime ideals as a modulo over A by P, just singleton P. That is clear because the only minimal prime ideal here is P, and other prime ideals, they contain a non-zero divisors. This is an integral domain, so they contain non-zero divisors, so they cannot be associated primes. All right, this is one. More generally, so further this is one. So this gives enough examples of a primary submodules, namely all prime ideals in a ring, they are primary submodules of this, but they are not all. So if Q is P primary ideal, now instead of saying submodule we will say ideal in A, then obviously Q will be contained in P, and this Q will contain a power of P for some N. This is very easy, and it follows from the following observation that if Q is P primary, if and only if the associated primes of A by Q as A module, this is only P, and therefore we know the nil radical is only one prime ideal, so the nil radical is P. So therefore from here it follows easily that if I take look at the ring A by Q, it has only one minimal prime, so the nil radical of this ring is intersection of prime ideals, which is, and only one prime ideal is required because this is the minimal one. So this is this, and now if P the ring is Noetherian, so therefore if P is generated by A1 to AR, then because this is the nil radical, therefore the power of this, so AI power Ni will become 0 in the ring A by Q, but that will mean that AI power Ni belonging to the ideal Q for some Ni. This is true for every N for every I from 1 to R, and therefore from here it follows that if I take capital N to be the maximum of N1 to Nr, it follows clearly that power of P, nth power of P, these all will be contained in Q, because when you take any element in P, write it as a linear combination of A1 to AR and raise it to the power N, Maybe you will have to, okay, maximal will work. So, when you expand the polynomial expansion, and then it will get all that, those elements will be in Q. So, that proves that fact that primary ideals have this property. But converse of this statement in general not true, converse is not true in general. That means if ideal Q is contained between P and the power of P, then whether Q is P primary, that is not always true, but it is certainly true when, but it is true if the prime ideal P is the maximal one. This is a set of all maximal ideals in A. So, this is easy to check. So, I will leave it for you to check this. All right. Now the next observation is a very important observation to prove what is called primary decomposition. And this is, so that means it's sort of given any subset, finite subset of the spectrum, can I find some module whose associated primes are precisely these given ones. So, that is this theorem. So, theorem. So, as usual, A is Noetherian ring, A Noetherian, and I have given now module V is finite A module. Finite may not be needed. So, I will just write A module here, and we have given a subset capital phi. This is a subset, this is not empty set, this is a subset of the associated primes of V. This is a subset, then subset, then there exists a submodule W of V such that associated primes of W is precisely the associated primes of V minus this subset, and obviously then the associated primes of A of V by W will be the given phi. Clear? So, we want to prove this. This is not so difficult. So, proof. So, we have given a module and given a finite subset of the associated primes, and we want to construct W, and therefore, we will construct V by W, and then we will check. So, now what do? You look at the family. So, look at the family. So, consider the family of submodules S. This is by definition all the submodules, those submodules P is a submodule of V, submodule such that the associated prime ideals of P, of the A module P, is contained in associated prime ideals of V minus that the given set phi. Look at this family. And I want to now look at the max. I want to choose a maximal element in this family with respect to the inclusion. So, that means I need to apply John's lemma to this family. So, to apply John's lemma, to the family, to the ordered set S with respect to the inclusion. I should check that I can apply. That means I should check that this ordered set is inductively ordered. That means I should check that given a chain in this, it has an upper bound. So, let C contained in S be a chain. Chain means totally ordered subsets of these ordered set. That means any two elements of C are comparable. Then look at P0. P0 is by definition union of all the elements which are occurring in this C. So, P where P in C. See, elements of C are elements of S which are submodules with some property. So, now we look at this P naught, then obviously this P naught is a submodule of V. That is clear because each P is a submodule and this is a chain. That means given any two elements here, I can always find an element, both the elements contained in the same P, and therefore I can add there. So, it is a submodule, is very easy. So, for this we need C is a chain. Alright, now I want to check that if P, so if P belonging to the associated prime ideals of P0, then I want to check that, so this means what? That is P is the annihilator of some element in P. P is the annihilator of X, so X is in P0. And obviously X has to be non-zero. So, take such a element P, therefore, this X will belong to P for some P. So, that will imply, because this P0 is a union, so X will belong to some P with P belonging to C, and therefore, this P small p will belonging to the associated prime ideals of V minus phi, because any, so this means that this P actually belong to the associated prime ideals of P, but associated prime ideals of P is contained in this set, therefore P is contained there. Alright, so we have checked that if P belong to the associated prime ideals of P naught, then P should belong to this. And also note that I forgot to check that this is an S is a non-empty set. That is clear because the set 0, the submodule 0 submodule belong to S. That is clear because P is 0, then the associated prime ideals of 0 is obviously contained here, and therefore 0 is an element in this, therefore this is a non-empty set and chain has an upper bound. And now we want to check that this P naught is the required submodule, but that is clear because we have checked that this P, every P is contained here, and therefore so therefore what we need to check is the following. Alright, so we have checked that, what we have checked that is associated prime ideals of this, the union P naught is contained in associated prime ideals of V minus phi. This is what we have checked. So now we pick up a maximal element there. So we check that this ordered set has a maximal element. So let capital W be in S be a maximal element. With respect to the inclusion, and then I want to check that. So we want to claim that associated primes of A V by W is actually contained in phi. This is what we want to check. Actually we want to prove here equality, but I am checking this first. Then what will happen once I check this, then associated primes of V, which is contained in the associated primes of W union associated primes of V by W. This will be contained in, this is contained in associated primes of V minus that phi, that is how we have chosen that maximal element, and this is contained in phi. So this is union phi, and therefore we will, so this will prove the theorem. Alright, so we have to prove that this inclusion, this is what we need to prove. So let P be an associated prime of the residue class module, but that means so that is there exists an injective module homomorphism from A by P to V by W, because this P is an annihilator of some element, so that will give you this inclusion. And let n prime, so let us look at the, so this is a submodule of this, so submodules of these are precisely the residue class modules. So therefore look at n prime, so this is phi, then I am looking at V prime, a submodule of V, with the property that A by P is actually isomorphic to V prime by W. So this is a submodule which contains W also. This and because now look at this this quotient module is isomorphic to this. So therefore the associated primes of V prime by W, this is only singleton P, because that is same as associated primes of this and singleton P. Therefore associated primes of V prime, which is contained in associated primes of W union P. This is again we have applied the observations what we saw it earlier, and therefore so this will prove that associated primes of V prime is contained in associated primes of A V minus that given set phi. This will happen when, so say when W is not maximal. In S. So therefore it follows that P belonging to associated prime ideals of V prime will be contained in associated prime ideals of V, and therefore P will belong to phi. P must belong to phi. So that proves the theorem, and this is very important theorem, and we will continue this to prove that every submodule of a module has a primary decomposition. So I will define, after the break I will define what is the primary decomposition, and then we will prove that every submodule has a primary decomposition.